Hi everyone! In this video we're going to start our chapter on nuclear magnetic resonance, or NMR spectroscopy. So NMR spectroscopy is another analytical method that we can use to figure out the structure of an unknown compound. Now down below I have a picture of an NMR spectrometer. So you can see that the person standing next to the spectrometer is on a step ladder. So these are pretty large instruments. Now they can be smaller or even larger, kind of depending on the strength of the instrument. Now these instruments are using magnets, so it really depends on the strength of the magnet. So basically what you do is you place your sample into a special tube, and then you drop the tube in between these magnets. And then we use signals to kind of probe the molecule and see what types of atoms we have. And then we detect them, and a computer will turn all of that information into an NMR spectrum. So in this spectrum, you can see that we're looking at the different types of hydrogens on the ethanol molecule. So we have our alcohol proton, we have some green protons that are on that middle carbon there, and then we have some protons that are on the very end of the molecule. And they all generate different signals. So we'll talk more about that later. Now, you could also use NMR to figure out how many different types of carbons you have. You could also use this on nitrogen or phosphorus, pretty much any atom that has a nucleus or an isotope with an odd number of protons and neutrons. So let's talk about that a little bit more. All right, so in NMR spectroscopy, we're looking at the nuclei of atoms. So remember that nuclei contain protons and neutrons. Now specifically, we're going to look at nuclei that have an odd number of protons and or neutrons. Okay, so why the odd number? Well, nuclei have a property of spin. So this is kind of similar to when we talked about electrons during our quantum mechanics section in general chemistry. We said that electrons can have spin up or spin down properties. This is kind of similar to nuclei, but instead of electrons, we're talking about protons and or neutrons. So let's say that we have a proton nucleus, so it's just a positive charge there. It is an odd number of protons, and we don't have any neutrons, so this does have the property of spin. Even numbered nuclei do not have this property. All right, so when this proton spins, it generates a magnetic field. So if you've taken physics, you probably know a lot more about magnetic fields than even I do. It's been a while since I've thought about these. But this will generate a north and a south end, very similar to just a regular old magnet. So that magnetic field is generated by spin. So that's kind of what I'm showing off to the right there. We've got some nuclei with different spins going on. All right, so then how does NMR convert that into a spectrum? So because these nuclei have a magnetic field, we can apply an external magnetic field and see if the nuclei align with the field or align against the field. All right. Now, a second magnetic field that's perpendicular to the nuclei will knock them off axis. And I'll show you a little diagram of what's going on in a second. Okay, so let's say that we have some nuclei. They're all just kind of pointing in different directions. And then we apply an external magnetic field that's very distinct. Those nuclei can now either align with the magnetic field or against the magnetic field. And once they're aligned with or against, another magnetic field that's perpendicular is going to come in and kind of knock down these aligned nuclei. So what this would kind of look like, let's draw an X, Y, and Z axis. All right, so we've got X, Y, and Z. So these are our 3D coordinates. And let's say our nucleus is aligned with the Z axis. So it's pointing up. The external perpendicular magnetic field is going to knock down the electron so that it's kind of pointing along the y-axis or the x-axis, depending. And then after that happens, the nucleus wants to go back to its original state. So it's actually going to kind of circle back up to its original alignment. So it's kind of like those toys where you knock them over, but you can't quite knock them over all the way. And then they just kind of naturally tip back up to their original position. I think it's like Weebles wobble, but they don't fall down. That's kind of what's happening here. Hopefully you know what I'm talking about. But anyway, as the electron kind of squiggles its way back up to its original alignment, we call that the relaxation pathway. Okay. So now the instrument is going to read that relaxation pathway, and we end up getting what's called a free induction decay. And don't worry too much about this information. This is stuff that you'll learn again later on if you take higher level chemistry courses. But the signal kind of looks like a little wave, and then it decays as you go along the x-axis. So again, this is called free induction decay. And it's abbreviated FID. So the x-axis is time, and again, we're reading that relaxation pathway. And then we're going to use something called Fourier transform to convert this FID signal into a readable spectrum that we can interpret. So that will give us our NMR spectrum. And again, don't worry too much about Fourier transform and the free induction decay. That's all stuff that you'll learn later on if you continue to study this. But the NMR spectrum is going to be read in parts per million. So we'll talk more about that later. Okay, so now let's talk about how to prepare your samples for NMR. All right. Now, in order to acquire your NMR spectrum, you're going to dissolve the sample that you're analyzing in a solvent. Now, the solvent has to be somewhat different from your compound, right? You don't want to get any interfering signals. So let's say, for instance, you're performing proton NMR. You don't want a solvent that has protons because then you'll get readings from your solvent and your compound. So the solvent should not have protons. So instead, we're going to use deuterium. So that is hydrogen with a mass of 2. So this is an isotope of a proton. And we're using this to avoid any solvent signals. So luckily deuterium has a range outside of the range that we would read for protons. So the deuterium signal won't show up on our NMR spectrum, or if it does, there'll be a single peak that we can calibrate against. All right, so the solvents that we're going to use are called deuterated solvents. And some options would be chloroform, which has 3 chlorines, and then we would replace its 1 hydrogen with a deuterium. You can use methylene chloride, where the hydrogens are replaced with deuterium. You could also use benzene, where all of the hydrogens are replaced with deuterium. And then you could also use deuterium oxide, which looks like a water molecule with 2 deuteriums instead of hydrogens. So the way that we would signify that these have deuteriums instead of hydrogen is you can put a lowercase d next to the name. And then you would also add how many hydrogen or deuteriums you have. So we have methylene, chloride, and we'll just follow that with D2 to say that we have 2 deuteriums on there. Benzene, we'll say has 6. And then the last one we're just going to call deuterium oxide, so we don't have to put the lowercase d on the end. All right, so once we've prepped our sample, we're going to put that into one of those special tubes for NMR, and then we're going to drop that tube into the NMR instrument. Okay, so now let's figure out how many signals we would expect to see once we analyze a sample. So again, you could use either carbon NMR or proton NMR. Oops, I meant to write a 1 and then a hydrogen. There we go. And there's other isotopes that you could analyze as well. But these two are the most common since most of the samples we're looking at have primarily carbons and hydrogens. All right. Now, regardless of which isotope we're looking at, nuclei that are in the same chemical environment will have the same frequency. And we call that frequency resonant frequency. So what is this resonant frequency? Well, that is the frequency that knocks the nuclei off axis. So as an example, let's say we're doing proton NMR. So we're trying to analyze the hydrogens. And let's say we're looking at the following molecule, methylene chloride. And this time there's hydrogens. So would you say that those hydrogens are the same or different? Are they in similar environments or are they in different environments? So the hydrogen that's on the top, it's bonded to a carbon that's bonded to two chlorines. The other hydrogen is also bonded to a carbon that's bonded to two chlorines. So they're both in the same chemical environment. So I'm going to label both of these as hydrogen A. Now another way to look at this molecule does have a plane of symmetry. So those two hydrogens are the same. So let's just make a note. The hydrogens in CH2Cl2 are equivalent. And that's because they are bonded to the same carbon and there's a plane of symmetry. Okay. So let's try another one. Let's see if we can figure out how many different hydrogens there are on a different molecule. All right, so let's draw the following diethyl ether. Oh, I don't know why my pen suddenly went bold. That has no meaning. You can ignore the boldness part. Okay, so try to figure out how many different hydrogens we have on this molecule. So again, are the hydrogens bonded to the same carbon? Is there a plane of symmetry? That will all help you determine how many hydrogens you have. So you can pause the video, see if you can figure it out. And when you unpause, we'll go over it together. All right, so I'm going to start on the left-hand side of this molecule. And all three of the hydrogens that are bonded to that carbon on the very far left, those are all the same. So you can kind of think of it as if we have a singly bonded carbon with these three hydrogens, remember that single bonds can freely rotate. So these hydrogens are all rotating around. So it's really hard to tell the difference between them when they're all bonded to the same carbon atom. So we could label all of those hydrogens as hydrogen A because they're all equivalent. All right, what about the hydrogens on the second carbon? Are those the same as HA? Are they different? Are they both different? Are they completely different from each other? Well, those two hydrogens are bonded to the same carbon, so they will be equivalent to each other, but are they the same as HA? No, because they're bonded to a carbon that's in between an oxygen and a carbon. So their chemical environment is different from HA. So we're going to call these HB. Okay, now let's go to the next carbon and its protons. Are those protons going to be entirely different from HA and HB, or are they equivalent to one of those two? So notice that there is a plane of symmetry in this molecule. It kind of goes right down the center there, right down oxygen. So we're sort of looking at the mirror image of the left-hand side. So that tells me that the two protons there are the same as HB on the left. And the hydrogens on the very end are all the same as HA on the left. Okay. So again, all of the HA hydrogens are in the same chemical environment, and then all of the HB hydrogens are in their own chemical environment. So it kind of depends on what carbon they're bonded to, and then what those carbons are bonded to. All right, so that means we would have two signals on our NMR spectrum, specifically our proton NMR spectrum. So one for HA and one for HB. All right, let's try another one. So this time we're looking at an alcohol. See if you can figure out how many signals we would find on the NMR spectrum for this molecule. And feel free to pause the video if you want to try it on your own first. Okay, so let's start on the left. And those three hydrogens bonded to carbon, we said would all be the same because they're bonded to the same carbon. So we'll just label all three of those as HA. Now let's move to the middle. So let's look at the two hydrogens bonded to that carbon that I drew an arrow towards. Would those be the same as HA, or would they be different? They're different because that carbon they're bonded to is different from the other carbon. It's in a different environment. So we're going to call those HB. All right, and then finally we have our alcohol proton on the very right-hand side. Is that similar to either HA or HB, or is it completely different? It's completely different. It's bonded to an oxygen instead of a carbon. So that would have its own signal as well. Okay, so that means we have three signals for this molecule. All right, so we'd have a signal for HA, a signal for HB, and a signal for HC. All right, so let's do a challenge problem. Okay, so I'm going to give you a molecule, and I'm not going to draw the hydrogens this time. But I want you to figure out where the hydrogens are on this molecule and whether you have one signal, two signals, or three signals, etc. So how many different hydrogens are there on this molecule? And remember to look for planes of symmetry. So feel free to pause the video and try this on your own first, and then we'll go over it together. All right, so let's draw all the hydrogens on this molecule. Now, one thing I'm going to do is instead of drawing the pi bonds in the benzene ring, I'm just going to draw a circle, because remember those pi bonds are actually delocalized all the way around the ring. And I want to just make sure that the hydrogens we're drawing are actually reflective of their environment. Okay, so now we have a tert-butyl group up above. All right, so we've got those three carbons kind of pointing out. Each one of those carbons has three hydrogens. Okay, same thing on the bottom. We have a tert-butyl group, and each of those three carbons has three hydrogens. So it's starting to look like a little tree here. Now on our benzene ring, we have one hydrogen on each carbon that's left. Okay, so do we notice any planes of symmetry? That'll make it a little easier to assign the hydrogens. So I do notice one kind of through the middle here. Okay. Are there any other planes of symmetry? So if we were to look at a tert-butyl group, just kind of off to the side, the carbons, remember, are kind of similar to those hydrogens we talked about earlier. They're all bonded to one carbon. So these can all freely rotate around. So that means those three carbons are all the same. They're all in the same chemical environment, and it's really hard to tell them apart from each other. So we can extend that to all of their hydrogens too. So all of the hydrogens that are coming off of those carbons are rotating as well. So they'll all be the same too. So there is a plane of symmetry going down the middle from top to bottom as well. So there's two planes of symmetry. Okay, so kind of thinking about all of those rotations, I'm going to highlight these three hydrogens in blue, so they're all the same. And that would tell me that the hydrogens off to the right are the same. And then the hydrogens up above are also all the same. So we'll call those hydrogen A. Now, remember there was also that horizontal plane of symmetry. So down below, all of those hydrogens are also the same. They're all in the same chemical environment. Now, what about the hydrogens that are directly bonded to the benzene ring? Are they all the same? Are they different? Well, they're definitely different from the A hydrogens, but they're all the same to each other. So I'll highlight those in purple, and we'll just label those B. Okay, so we have two unique hydrogens, or types of hydrogen. We have HA and HB. And I'll just highlight those so we can keep track. Now, what would this look like on an actual NMR spectrum? Well, I told you earlier that on an NMR spectrum, we measure the peaks in parts per million on the x-axis. We'll talk about why later on. But the signal for HA will show up just past 0. And we do have 9 of those, or sorry, 18 of those. So the peak for HA is going to be bigger than the peak for HB because we only have 4 HB protons. And those would be found kind of in between 5 and 10 ppm. So they would be sort of in this region. And again, there's only 4 HB protons. So the peak for HB will be smaller. All right, so the amount of protons that you have, so for instance, we have 18 HA protons, that's going to affect the size of your peak. So if you have more of a certain type of proton, that peak will be much taller or have a greater area underneath. All right, now before we go, let's do an extra difficult challenge. Okay, so I'll give you an extra difficult molecule. All right, and let's see, there's also going to be some chlorines on here, and then a bromine as well. So we're kind of mixing it up a bit. All right, so again, try to figure out where your hydrogens are on this molecule, and then try to figure out if they're in the same chemical environments, if they're in different environments. Also try to figure out if there are any planes of symmetry, because that will help you identify the chemical environments. So feel free to pause the video and then we'll go over it together. All right, so first of all, let's see if there's any planes of symmetry. Do you see any planes of symmetry? No, I don't see any planes of symmetry, so that's going to make things a little more difficult. Okay, now let's figure out where all of our hydrogens are. So we do have 4 hydrogens on the benzene ring. Let's see, then we have 2 on this carbon, and I'm going to show them as wedges and dashes. And then we have one kind of hiding behind the bromine there. Okay, and I think that's all the hydrogens we have. So now let's look at, let's see, I'm going to highlight the first hydrogen. Okay, so I'm going to label that as hydrogen A. And then let's figure out if there are any other hydrogens that are in a similar environment. All right, now you might think that the one across from it is similar, but look at the bonds that it's next to. So HA is next to a single bond that's next to another single bond where the carbon is bonded to 2 chlorines. Whereas the hydrogen down below is bonded kind of similarly, but the carbon here is bonded to bromine, not chlorine. So they're actually in different environments. Okay, so I'm just going to highlight that in a different color. Okay, what about the hydrogens to the far left on the benzene ring. So let's start with the one on top. Is that similar to HA, or is it different? So that hydrogen is in a different chemical environment because it's on a different carbon and it's actually one bond further away from those chlorines. So that will definitely have an effect on it. So that is a different hydrogen. So I'll label that as HB. And let's highlight that in green. Okay. And then what about the hydrogen down below? Is that similar to HB, HA? Is it different? That one is also in a different chemical environment because it's bonded to a different carbon and it has kind of its own distance away from those substituents, chlorine and bromine. So we'll just label that HC, and let's highlight that in yellow. All right, and then I'll label the purple hydrogen, HD. I'm going to run out of highlighters here though, so I might have to stop highlighting soon. Okay, so now let's look at this hydrogen that's in a dashed position behind bromine. Is that similar to any other protons? Nope, it's in its own environment. It's bonded to a carbon that's bonded to bromine, but none of the other hydrogens on this molecule are in a similar position. So that gets its own letter, so we'll continue on with E. All right, and now let's look at these two hydrogens. So they're on the same carbon. One is in a wedge, one is in a dash. So are they the same or are they different? So my first inclination would be to say, oh, they're the same because they're on the same carbon. However, notice that the hydrogen in the wedge is syn to bromine, whereas the hydrogen in the dashed position is anti to bromine. So remember our elimination reactions? We talked about how for some elimination reactions to occur, you have to have a proton that's anti to bromine or anti to the leaving group. So that does mean that that makes a difference. The position is going to be different and the chemical environment is different. So actually these two hydrogens are different from each other even though they're on the same carbon. Kind of crazy. Okay, so let's kind of write down what we've learned so far. So on this molecule we have 7 unique hydrogens. And HF is unique because it is syn to bromine. Hg is unique because it is anti to bromine. So these are all things we have to take into account when we're trying to predict how many signals we're going to expect. But the opposite is true as well. We're going to end up with 7 unique signals on our NMR spectrum. So maybe one signal is due to the hydrogen that's syn to bromine and the other is anti to bromine. So things to just keep in mind. All right, now there is a term for HF and Hg. So HF and Hg are called diastereotopic protons. All right, so I'm just going to underline that. So one way that you can tell if you have diastereotopic protons is to replace one of the protons with deuterium and then compare. All right, so I'll show you what I mean by that because it might be a little confusing at first. So I'm just going to draw the molecule without all of the hydrogens. And then I'm going to show our wedged hydrogen as a deuterium and keep our dashed hydrogen as hydrogen. Okay, then I'm going to compare that to the opposite scenario where we replace the other hydrogen with deuterium. Okay, so I'm going to keep the wedge hydrogen the same, but the dashed hydrogen is now a deuterium. Okay, so now let's identify any stereocenters. So remember, a stereocenter is a carbon that's bonded to 4 different groups. So the carbon bonded to bromine is a stereocenter. And now that we've replaced one of the hydrogens with deuterium, that carbon can be considered a stereocenter, but only for the purposes of this discussion. All right, so now we can clearly see that the carbon bonded to bromine stays the same, but the other stereocenter has changed because we flipped the hydrogen and the deuterium. So when we're comparing these two molecules, they are diastereomers because only one stereocenter changed. So that means that the two hydrogens up above, HF and HG, are diastereotopic protons. So that's their relationship to each other. Okay, now let's look at some other relationships that can exist between protons. All right, so we can have what are called homotopic protons. So homotopic protons are chemically equivalent. So we saw that with our dichloromethane or methylene chloride molecule. Oops. So those two protons were the same because they were bonded to the same carbon and there was a plane of symmetry. You can also have what are called enantiotopics, or enantiotopic protons, excuse me. So if there is a plane of symmetry and you can create enantiomers, then you can call those protons enantiotopic protons. So they are, let's see, they are interchangeable by reflectional symmetry. It's kind of a fancy description. But let's look at an example. So let's say we have the following. Okay, so we have two hydrogens bonded to the same carbon, and then we have a fluorine in a wedge and a chlorine in a dash. Now let's replace one of those hydrogens with deuterium, and then we'll flip them. Kind of similar to what we just did on the last slide. So let's replace the left hydrogen with deuterium, and then we'll compare that to the opposite scenario. We'll replace the right hydrogen with deuterium. Okay, so now let's figure out the relationship between those two molecules. So carbon is a stereocenter in this case. It is bonded to 4 different types of atoms. And if we were to assign R or S, let's see, chlorine would have, let's see, first priority, Fluorine would have second, deuterium would have third, hydrogen would have fourth. Okay, so then, let's see, 1, 2, 3. So I think we'd have an R on the left, and then because we switched the hydrogen and deuterium on the other molecule, that would be an S. So these would be enantiomers, which means that those two protons are enantiotopic to each other. So in essence, we're kind of creating the mirror image, right? Okay, so now diastereotopic, we already saw an example of on the last slide. But diastereotopic, let's see, are not chemically equivalent. So see example on last slide. So they do exist in different chemical environments, and as we saw in the last example, they might be, for instance, syn to another functional group, or anti, which is what makes them different. But you can always do that replacement test to double check. So you can replace one of the hydrogens with deuterium and then flip them. See if you end up with enantiomers, diastereomers, or maybe they're the same. And then you can call them homotopic if they're the same, enantiotopic if they're the same but they're interchangeable by symmetry, or diastereotopic if they're not chemically equivalent at all. All right, so I introduced a lot of concepts in this video, so I'll stop here. Next time we're going to talk about those signals that I was showing you, and we'll talk about how to determine the number of hydrogens you might have in your molecule based on the size of the peaks. So I will see you then.